Let's learn about matrix operations, specifically some notation. Consider the matrix given here. This matrix has 3 rows, 1, 2, 3, and 4 columns, 1, 2, 3, 4. We often denote the columns with A1, A2, A3, A4 in this case. So this right here is column A1, right here is column A2, and so forth. This last one is column A4. And so we can then write the matrix A by just simply writing down its columns, A1, A2, A3, A4. We also give each individual element of a matrix a name. The elements of the first row are, this one right here is A11, the next one is A12, then A13, and then A14. So in the notation, we have 2 indices for each A. The first index indicating which row we're talking about, and the second one is the column. So let's look at the second row. The second row, all the elements in the second row start with a 2, and then the one in the first column gets a 1. The one in the second column gets a 2, and the third column is a 3, and the fourth column is a 4. So those are these 4 elements right here. More generally, an element in row I, so suppose this one is row I, and this one is column J, then the element in row I and column J will be denoted Aij. Here's a more general example. So this matrix has m rows, 1, 2, all the way through m, and n columns, 1, 2, all the way through n. The columns are also denoted A1, A2, and so forth through AN. I also wrote down a column AJ right here. And so we could write down this matrix by simply listing its columns, A1 through AN. Again, the element in the ith row, so here I wrote down the ith row and the jth column, that element in that particular location is called Aij. Let's go back to the original example of our matrix A. The diagonal entries of that matrix are those entries where the column and row have the same index. So this one right here, this one, and this one, those form the diagonal entries because this first one is A11, the next one is in location 2, 2, and this one here is in location 3, 3. Together, the diagonal entries form the main diagonal of the matrix. We can also speak of a diagonal matrix, which is a square matrix, so a matrix that has the same number of rows and columns, all of whose non-diagonal elements are 0. So the only entries that are allowed to be non-zero are those on the diagonal. Here are some examples. The first matrix A has the diagonal elements 5, 2, and -3. It's a 3 by 3 matrix because it has 3 rows and 3 columns, and everything that's off the diagonal is equal to 0. The second matrix B is a 4 by 4 matrix. The diagonal elements are right here. One of them actually happens to equal 0, but that's allowed as long as the non-diagonal elements are all equal to 0. And the last example is again a 3 by 3 matrix. The diagonal entries are right here, and everything that's not on the diagonal equals 0. This last example actually is a special matrix. It's called an identity matrix because all the diagonal elements are equal to 1. And a matrix of this form is called an identity matrix and is denoted by IN, where n is the number of rows and columns. So in this case right here, the matrix C would also be called I3. There's one more special matrix, which is a 0 matrix. And that's a matrix, all of whose entries are 0. It's simply denoted with a kind of a curly 0 right there. So there are many different 0 matrices depending on the size, and the 0 matrix does not have to be a square matrix. So the first example here is a square matrix. It's a 3 by 3 0 matrix, but the next one right here is not square at all. It has 2 rows and 5 columns. It's also a 0 matrix. So is this one here with 3 rows and 2 columns, and so is this one with only 1 row and 1 column. All of these are examples of 0 matrices, and all of them are denoted by the same symbol 0. So the context has to tell you what size 0 matrix you're actually talking about. There's actually a 0 matrix for any number of rows and columns. The symbol 0 does not reveal the dimensions of the matrix, and so the context has to make it clear what zero matrix we're actually talking about.